guide, hoping to get it finished next year. So just to let you know, this has been done as an ASHRAE MTG. So ASHRAE has formed these MTGs as a way of doing short-term projects. This won't last forever. Hopefully, we need to get this thing written. So a design guide is a good example of a short-term project, and the MTG exists while we do the guide. So it's like a TC, but it's got a definite life. And this one is the HCDG, it's a hot climate design guide, and it's here just to produce this design guide. We want to produce this for all areas that experience hot summer periods. However, we're really focusing on low carbon solutions and low energy solutions, and also dealing with natural cooling design as far as we can, although there will be hybrid. Just to remind you, ASHRAE already has a guide for hot and humid climates, so we're not really going to cover that field, although we will refer and mention to that guide. So just in terms of learning objectives, which is what we normally put up during a workshop, we want to understand the reasons why we need the guide now. So I've got some comments on that. We want to appreciate the task ahead. So we want to make sure we build all our new buildings in hot climates to be as near as net zero as we possibly can, and eventually to be net zero. We want to be aware of the strategies for constructing buildings in hot climates to be net zero from the outset. What kind of things have we got to do now? And then I want to really cover passive solar design alongside mechanical cooling. So we can use passive design in a lot of places, but at some point it struggles and we have to supplement it with mechanical cooling. So we call those hybrid solutions. But all too often, and you've seen this in North America, they just build the standard air-conditioned building, which operates that way as a mechanical system all year long. We don't have to do that. We can do hybrid. This can lead us to good cost savings, actually. So there's cost-effective opportunities which we can look at and show those to people. We also want to put some nice case studies in and some historic buildings that have worked well where we can to show people what has been done. And I think all the time we're doing this, we have to keep our eye on what we're really about, and that's about people. So we want to highlight the productivity and the health benefits associated with achieving comfort in hot climates. So the games, in terms of what the guide's going to have in it, and I haven't got a whole content list here, but I'm happy to share that with you. We want to talk about the aims of the guide. We want to so I'll go back one. The contents, what's in it, how does it fit in with other ASHRAE publications? We don't want to repeat material in the handbooks or elsewhere, but we do want to let people know there's bits and pieces around that can help them. I'd like to try and make this guide different, better, useful, like people to think it's been a well-produced guide. I think we all want that. Anyone who's been associated with it, and by the way, all the authors are acknowledged in the guide. And I do want to go into passive design, which is a little bit lacking in ASHRAE, but there's lots of good passive solar examples all around the world. And I'll highlight that today in this presentation that I've got here as part of this workshop. I want to talk about thermal storage because I think that's important as well. And certainly in some of those places in the Middle East, they are extremely hot during the day, but also quite cold at night. And so with a bit of energy storage, we can use nighttime cooling to help us through the following day. That might be simple passive cooling with materials, or it might be running chillers and heat pumps at night where they're more efficient, and then storing that cool for the following day. I want to cover daylighting and cooling landscape because they're all part of a successful design. Certainly, we do need to talk about air conditioning systems and equipment, and we're going to look at those. We have chapters, for example, on district cooling, how they're beneficial and much lower energy cost than traditional chillers located all over the place, particularly air-cooled chillers, which obviously struggle in a hot climate. As I say, we will be looking at hybrid sample systems and how we blend them in together and how they work together, and case studies. The contents will inevitably deal with weather and hot climates, and we have quite a lot of climate regions in the ASHRAE guides. They cover every climate region in the world, of course. So we want to certainly look at hot climates. I want to deal with external areas as well, not just cooling a building, but how do we cool parts of the building outside where people want to maybe sit outside in comfort, in shade, but in a hot climate. It can be done. it can be done effectively, efficiently, and at very low cost. It can be done for free, actually. So I want to develop that concept and show how that can be done. I'm sure people will come up with innovative solutions themselves, but also want to look at the indoor environment, of course. What do people want inside, and how do we achieve that? And again, linking this back all the time to productivity, people's comfort, better health, well-being, and safety. So we will make sure that those things are covered in there, and of course cross-linked to other ASHRAE sections in their guides, the handbooks, and documents. Standards, particularly, something we'll be looking at. Hybrid designers say lighting and daylight. It's very important that we maximise the benefit of free daylight. It's something that people like, of course. Want to deal with acoustics in here. It's a section that's important, particularly with cooling systems and heat pumps. If we have things like opening windows and heat pumps are running, they can be noisy. So how do we make sure that the noise levels inside the building are satisfactory, and outside for that matter? If people are going to sit outside in a comfortable, cool space that we've designed for them, we don't want to hear noisy plant and equipment running. As I say, energy use and carbon emissions has to be dealt with, and the bigger topic of sustainability and how we fit in with the Green Guide, LEED, BREEAM ratings, or whatever system people want to follow. But certainly looking at the issues that relate to sustainable development, and that of course relates to communities and how people want to live together in a happy, reliable, resilient um, community. So I thought it'd be useful just to remind us here that Death Valley is the place in the world where they recorded the highest temperature to date. It was 54.4 a couple of years ago. Very few people live there, of course. It is a desert, but there's quite a few people visit it. This picture is someone there on a day it was 59, so it can get extremely hot. But things happen. The Burning Man Festival is taking place usually in Death Valley. This year it's not in Death Valley itself. It's up the road in Black Rock City, Nevada, which is another desert, from August to September. So, these people these places attract people who like this rather extreme climate. And they go there for enjoyment, artistic, and that kind of thing. So Death Valley is what we call a dry air region. It's very low humidity levels, but very high air temperatures. Anyone going there would suffer from heat exposure if they're not careful. There's no shading, as you can see, and they need protection from direct sunlight as well. They could be damaging to their skin. But this is a picture from their website, which illustrates some people stood there just near their car park, obviously. So when we're looking at buildings in hot climates, they're going to need cooling, aren't they? And of course, a modern city looks more like this. Lots of glass. So you think, well, okay, heat is going to penetrate that glass and direct solar gain inside. So how do we make sure that's going to be dealt with? Because humans want comfort in their building in order to do their job, be productive. If they're too hot and they can't think properly, they're not going to be productive. So we need to avoid overheating. And to do that, we're going to provide cooling, we're going to provide air movement, and we will need to control humidity too, both in an over dry climate and also in a high humidity climate. So we have a range to work within 40 to 60% relative humidity. And that's the best range for people in terms of comfort. It also happens to be the most healthy range as well. That prohibits growth of viruses and bacteria. So we want a temperature-controlled indoor environment, and air conditioning would be the answer for that. So we will be looking at how we select and design air conditioning systems to achieve that. But the other issue that's happening is that we're getting rising temperatures worldwide. So you can see here that this is Kuwait, where Hassan came to my meeting this year in the summer, in June, and told us they'd reached 54 degrees C in Kuwait, the hottest they'd ever reached it. So Kuwait's hottest time of year is during the dry season, which runs from April to September. And during this time, daytime temperatures can regularly reach 44, although this year it reached 54. the summer season in Kuwait also brings high temperatures, increased humidity, and dust winds. So there's a whole load of issues which we have to deal with there, and how air conditioning is absolutely necessary, of course, but it will use a lot of energy. And that in itself adds to the whole climate change problem. It's making the planet hotter, so we're getting these hotter summers. So, how do we deal with that? Right. So just well, there's been a lot of discussion about how to deal with climate change. I just want to touch on this because it's one of the reasons we want this guide. Is we want to achieve these cooler buildings in cooler climates for people indoors, but we want to do it without using lots of more energy and really creating or adding to the problem that's really already there. So in Manchester, they had a green summit. The mayor set a target for that city to be net zero by 2040, and he's seeking out to the citizens of the city and others to do that. So it's a big deal. It's not easy, but this is typical of many cities around the world that have set these targets because they see the importance in what we're doing as engineers. Of course, they need to come up with the money and give us the instructions to allow us to do our job, but there does seem to be a willingness at least to start going in that direction. Manchester's an interesting city because it has the Tyndall Centre there, which is a big climate change research centre, world famous, and they do lots of research. I dipped into this recently just to see what kind of things are happening. And this is some of their programs looking at decarbonisation of the global environment in order to meet the Paris Agreement. What would be the impact if we do find that world temperatures rise above 1.5 and even above 2 degrees C? Because the Paris Agreement really said we've got to stop the world rising above 1.5 because that means we slip into fairly catastrophic events and more serious climate. So that's our target, is to keep below that. It's a slow moving thing, of course, but a lot of momentum, and we're moving that way. And what would be the implications of the Paris Agreement in itself? And some of these reports are quite interesting. So, for example, with a 3 degrees C rise around the world, we'd have cities like Miami on the left there completely flooded. We're actually going to get coastal flooding with the 1.5 degrees C rise. So by the end of this century, it's predicted that sea level rises will be 1 meter above where they are now. So that's going to certainly affect, well, certainly many cities here in the UK. And in fact, 50% of the world's cities are actually built on the coast for obvious reasons. We like living near the coast, and that used to be the way of transporting things. So it's an issue we have to think about, and we are going to touch in here on aspects such as rising sea levels and how we deal with that in our buildings to make sure our infrastructure is resilient. This is a project called Image. It's an integrated model to assess the global environment, developed by the Dutch under an EU funded project. And it kind of simulates environmental consequences of human activities worldwide. So work going on like that. And then there's this Ramesses one, which is looking at how energy affects sustainable development of cities. And I thought it was interesting to compare London on the left in 2018. That's a particular London city centre view you can see there and the kind of buildings we have against Granada on the right. That's the main centre of Granada, a much more traditional building, much lower energy, and yet a much higher summer temperature. Granada can reach 50 degrees C, but that's traditional build, you see. So can we go back to that? And then we have the issue of getting the energy that we need to do these things, moving away from coal mining, coal burning power stations, and indeed fossil fuel power stations generally, towards more renewables and maybe the use of nuclear. So there's been a big study going on what people think about that, because it does mean more pylons. Big issue in the UK at the moment is solar farms going up where we grow things, which is not a great idea in my opinion, but you have to give the land up to one thing or another. So there's lots of issues, and there's research going into what people think about that and whether they accept them. And indeed, cities like Manchester are coming up with these strategies on how to achieve these things. UK and European building regulations are strange at the moment because they only really cover environmental energies, all the stuff we use in buildings: heat, light, cooling, hot water, ventilation, but not really plug loads and not process loads. Whereas ASHRAE, in all the work we're doing, in our standards, we cover all energy use. So the PUI and other figures that we use are for all energy consumption. So that's the buildings. And in order to be net zero, by the way, we really have to make sure all those things are net zero carbon producers. And I've listed a few there. There's more information around on the things that could be included. And we would want to do that in ASHRAE by being lean, being clean, and being green. So being lean is really making sure that our building is efficient as we can make it, and then being clean by making sure that our systems that we use, and our engineering systems, are efficient and effective, and then being green by adding energy supplies which are developed from renewables or maybe waste energy from another process that we can use in our building. So these are our three major steps. We're going to get the building right first, our energy engineering systems to supplement that, and then green technologies last. So, and that, I think, is obvious to most of us, but some people are not dealing with it that way. They've got a pretty awful building, but they just want to buy green energy to make sure they're net zero. That's can be done, of course, but it's not the best way, not best use of money. Now, we got case studies of these around the world, and we can comment on them. That's the Bullitt Center in Seattle on the left. Interesting one there because the roof design has been made big enough, and you can see it overhangs the building on all sides by about 6 meters. It's been made big enough to catch enough solar energy to make that building net zero. The one at the bottom is Hawaii Research Center, and that's got two massive arrays of solar panels. Probably cost more than a building, I think, in order to make that net zero. Again, I would question whether that was financially viable. Obviously for a research center, they can do this kind of thing. The building above with the small solar panels integrated into the glass in this atrium roof is a Blackpool Visitor Centre, which is one of my projects, and we use those small panels to generate electricity, but also to provide a frit-in shading to the Blackpool building and keep this atrium cool. Well, otherwise it would have been obviously too hot just with glass on. And the building on the right is an office building in La Jolla in California. And the interesting thing about this is that it looks pretty normal. It looks like an ordinary building, but it's using methane waste gas to generate power. And that power is producing heating, electricity for the building, and also cooling through absorption chillers and heat pumps. So you can have a fairly traditional build if you like, but you can do some clever engineering systems to make it zero. How would you achieve net zero in some of these places, like London, for example, an enormous city with lots of buildings of different types and shapes and sizes and ages? We can't demolish all those, of course. It's got to be done some other way, and that's something we're working on. And you can see here a typical picture of London. This is a model of London in one of the museums, and on the right, some of the traditional buildings. These are all listed, by the way, but incredibly expensive, and they're not highly insulated or anything like that. So we have to come up with solutions which will enable us to retain these buildings, but become net zero. This is another typical high street, and I found this place with my name on it, although it's not mine. And this is typical of many London suburbs. So here at ASHRAE, we've been producing the Advanced Energy Design Guides, and we will mention those in the guidance we're producing so that people can refer, for example, on how to do them. We also want to pick up on passive solar design. This is two examples, Dragvoll universities in Denmark, where they've used a passive atrium here to help shelter the buildings on either side, but also bring in solar energy passively into the space. So it's preheated space, and also helps to ventilate the building either side of it. And this idea has been tried in the UK quite a lot. This is the John Darling Mall. It's a school, and you can see this provides sheltered space for students. On this particular day, it's sunny, of course. On other days, it could be raining, but it's a useful space. It's not part of the teaching area, though. It's semi-external. It's not deliberately heated, but it will be a warm space by due of the sunlight it's capturing. There are methods that we're talking about in the guide, and we're showing people how to use them, such as the LT method. This stands for lighting and thermal method. It looks at the glass and the fabric used in a building and what the balance should be. And this was really developed by Cambridge University. It's an energy design tool. It's simple to use. It's not specifically computer based, although it could be. So it's a first stage strategic analysis to help guide somebody into an efficient design. It was developed using EU Directorate money at the time, and it's aimed at non-domestic buildings, but it provides some really good checklists and tables. And so we'll be making reference to those in our guide, and they'll help people, without having to switch on a big complex computer program to know in which direction to move with their design. And we can then talk to architects and planners about best orientation and so on. The other area which is quite useful is this handbook of tropical housing and building design. It's really for strategic analysis, showing forward analysis thinking, synthesis and evaluation. And again, it's manual calcs and fairly easy to use, first stage work, but it will get us towards the design we want before we have to start doing complex computer analyses. It relies on climatic data, and of course we have a lot of that in ASHRAE, so we'll refer to where the climate data is, but local climate data is what's really used here, together with something called the Mahoney tables. And in the tables themselves, we have some indicators which will enable us to think through how the building should be planned and developed and what kind of systems we want. So typically it talks about the layout, the spacing between the buildings. By layout, I mean, does it point north to south, east to west? Are we having close groupings, or we have them spread out? What kind of height, orientation, and so on? We look at air movement around and between the buildings, and what kind of openings we want in our building. Windows, doors. But it could be more complex. Could be roof outlets, could be chimneys, and there are lots of other ways of getting air into and out of a building. And so we can work through those on this analysis and see which the best solutions are. And we will obviously look at the properties of the walls. We want them well insulated. Do we want heavyweight? Do we want lightweight? And what about the roofs? The same again there, and also looking at rain protection. So the other thing the Mahoney tables brings out is the fact that in hot climates, they're not always hot. Climatic conditions will vary. So we've got to look at a solution that works through the whole of the year. So seasonal requirements may contradict, in fact. So what we're trying to do in a hot period may contradict what we're trying to do in a cool period or a windy period. So we need to prioritize that, and we need to take account of the severity and the duration of climatic factors. But always remember, occupants must always be comfortable every day. We can't sort of say there's some days when you can't use the building. That is not an answer. But we as engineers know there's some periods are more severe than others, and we've got to solve those as well as getting the others right. So daytime, hot, dry air, hot, dry ground temperatures could be anything between 27 to 54 and maybe even more. Daytime temperatures above skin temperatures is bad, because that's uncomfortable and possibly damaging. And then we have to think about the nighttime. Do we have cool night times? Do we have cold, dry air? Do we have clear skies? Because that would be able to emit heat away from the building into the sky, and be lost out of the earth. Or do we have cloud cover? So heat loss by radiation and into any cool air, the wind, the convection that's happening is important. We need to know how much that is affected during the day and at night, and what kind of humidity we would deal with during those 24 hours. Does it change? Is it moderate? Is it low? Are there periods of high humidity? We're not designing for high humidity because that's done in the other guide, but we would want to identify that and refer people to the other guide for those periods. Where we have low rainfalls, of course, that leads to barren land areas with little natural shade. this is kind of example of it. I had a photograph. This is in Grenada, actually, a building which is interesting when you look at it because it's got a lot of hard standing outside the building. There is some attempt at shading. These trees will produce some leaves at some point, but they're quite small. And then we have a car park there. So when the sun is shining down, all of this hard standing and the cars themselves will be reaching temperatures of 60 degrees centigrade or more. And of course, they'll be warming the air up, which is then going to try and move into the building through these windows, or if it's a sealed building, through the air handling plant. So by surrounding the building with hard stand, we really are giving ourselves a major problem, whether we're looking at natural cooling or mechanical cooling. And we really need to think more carefully about the surrounding landscape, and particularly where we put cars. Car parks could be undercover, it could be multi-story, but it should definitely be away from the building because car surface temperatures can be very hot. You can burn your hand on a car in summer. So this is looking at one of the Mahoney tables. It's asks you for location, longitude, latitude, and altitude on your building. You enter that sort of information. Table 2 here, it divides the area into humidity groups. So I'm skipping through these fairly quickly because the Mahoney tables is a subject in itself, but I will be dealing with that in the guide, and we have some authors helping me to do that. Because I've found this quite useful understanding how climate and buildings interact. Particularly gets helpful when you start thinking about this external cooling in combination with the building itself. So it's got 4 humidity groups, and it looks at average mean temperatures, which you obtained from one of the earlier tables, actually. So the table results roll over from one to another. And then it gives you for day and night different ranges to work in. So from that, you can identify your building into one of the humidity groups and one of these average mean temperature headings. Table 2 looks at different indicators for humidity, and it divides the climate into 3 different humid climates and 3 different arid climates. So in the example that I've been working on, this particular building is ticks all the buckets for arid 1. So it's a very dry climate, hot climate, and it ticks some of the arid boxes in the summer and the winter, but it doesn't tick any of the humid boxes. So it's a generally quite a dry, arid region. And then we want to go into design indicators for the building, and we look at the layout, spacing, air movement openings, and also looking at the walls, the roof itself, whether we have outdoor sleeping. The Mahoney tables are generally aimed at housing, actually, in tropical countries. And if we have that, with rain protection. So people would have outdoor sleeping where it was cooler outside or there was a night breeze, and get a better sleep than being inside the building. For openings, the orientation would be based on a couple of factors, like the breeze prevailing in a hot, humid season, so that you get a cooling effect from that breeze, or else towards the sun during the cold season, so that we get a beneficial effect of sunshine in the colder season. Examples of those kind of issues coming to the fore would be in this Granada street scene. The buildings are fairly heavyweight, close together, a lot of natural shading being provided from one building to the one next to it. These are some shopping streets in that area, and you can see it very, very close together. There's obviously a wind tunnel effect, so wind will be moving down there, providing free beneficial cooling, but it's stopping the sun penetrating and overheating these spaces. The other thing is how people can use devices such as this shading. They do require constant attention because the sun is moving around, but the waiter here, he's taking an order 1 minute, another minute he's adjusting the overhead shading to put it somewhere else so that it's tracking the sun, if you like, keeping people in comfort. And as long as they're in shade, they're happy. So this is part of what we need to think about. We can produce designs based on sunlight coming in through atria roof, or diffusing in through diffusing glass, such as solar plex, or bouncing off of walls and surfaces so that the get deep into the room, and the more daylight we can get through, and daylight, blended daylight, the better, because that will give us a good, bright quality interior without using electrical energy. Although I appreciate LED lamps are much lower energy now than the previous time we were doing this sort of work, but it's still important to get natural light in where we can. This is an interior shot of that particular building. This is a university in England, De Montfort, and we did a lot of analysis on that particular project, which has got built. As you can see, it looks like this, quite attractive, really. But it's the light coming through that is adding to that. Also looked at how air moves through these buildings with atrium driving force. So the atrium is really driving the air upwards, like a big chimney in the middle of the building. It's sucking cool, fresh air in via the perimeter through opening windows, in this case, and keeping the building nice and cool. Now I use this analysis on a building in Sharjah. It was American University, actually, and we found that air-conditioned building could actually be naturally ventilated for 6 months of the year, because the external climate was very nice, actually. Air movement, day and night, would cool the building down, particularly night cooling, of course. And then the following day, the building would be comfortable to work in. Once the summer came, though, in Sharjah, we had to go to full air conditioning. But it's a big step forward if you can reduce mechanical systems to 6 months operation. A similar big project in the UK is this school in Burnley, in Lancashire, which is one of my projects. This was knitted into the hillside. You can see there, it actually points northeast, but by integrating it into the ground on a sloping hill, we managed to make natural ventilation work throughout. There's a large central atrium street, 160 meters long, and the building width itself is 180 meters. But each of these wings of the building pulls the air along the wing through the classrooms into the central atrium, which then is used as central chimney, if you like, to pull it through. One of the benefits of doing it this way was we're able to use ground coupling with thermal buoyancy. So where the building sits into the ground, you can see these void spaces below. There's 3 shown there. So the air was sucked through that void into the occupied building, and then cooled the classrooms, and then went up into the atrium out to the roof. So this blue illustrates where the void is, and how it comes through into quite a few. There's over 300 rooms in the building, but they're all tapped into these void spaces, and then the air is pulled out by buoyancy into the centre and out to the roof. So it's been quite successful. We validated our design at the time by using CFD, as you'd expect, to make sure the airflow was right and the temperatures worked. And this is a picture of that central atrium space where the air came through those doors you can see there, spilt into this space. And this was really one of these adventitious areas which wasn't deliberately heated or ventilated, but benefited from what was happening in the voids around it. The school decided to put a theatre space in there, but that's worked extremely successfully as well. And then looking at the Alhambra in Granada, a place to visit, it's a great example of passive design because it's about 500 years old, certainly constructed before we had any electricity or mechanical systems to help, but works extremely well. And it kind of picks up on a lot of the points that we're looking at in the guide. For example, the soft planting around the landscaping, so that any solar gain hitting the ground in the area is absorbed by the plants that need that, of course, and the air is then cooled to come into the building around it. Inside the building there, they've used trees for local shade and creating cool air. As I say, surrounded by that soft landscape, the gardens, the farmland, and it limits this heat island effect that we tend to get. The Alhambra is actually just on the edge of Granada itself, as you can see here. But big heavyweight buildings, you can see by that wind tower. And there's sheltered walkways that people use to get from one part of the building to another. And all this design, of course, keeps the stone there fairly cool in itself. We have courtyards with shade and water where people can sit and talk, relax, have a coffee. You can see people up at the windows there, so there's no glass, although the window's open, so So there's no glass to keep it cool and air conditioned. It's relying on airflow from outside. And another common aspect there is having cloistered walkways so that people get the benefit and water spaces as seen here. And also I found there people do rely again on moving shades. So this is an example of a restaurant there where these shades above can be drawn back or forth during the day to make sure that people below them are kept cool and in the shade and very comfortable. They enjoy this space. The wind movement is reasonably strong, so they have a breeze across them. I want you to just finish by looking at some air-conditioned buildings in Houston when we had the meeting there. I think that's 2018 now. Sheila Hayter was our president at the time, but that's a very, very modern city built in Texas with modern materials. It doesn't really, look very much like Granada, of course. But this is the way things are done. And there's nothing wrong with it, of course, but we need to think a little bit about our other ways of doing things, don't we? About the links, I will make sure that everybody gets the links. Or if you can put that in, we'll send links about this. So I had a question about the links, and you'll get those. So
Fantastic.
looking at Houston, this is a view from one of the big buildings looking down into the square there, and then right at the front there's this big electrical section which is taking the power into this part of the city and distributing it to the buildings. I think that's one of the first things that someone like me notices in some of the big American cities I've visited. They have quite enormous electrical demands to soothe their air-conditioned buildings, and these things are very visible. They have to be really because of the amount of power that's being delivered. And without that power, these buildings would be uninhabitable. I mean, our conference was very successful, but it wouldn't have been if the air conditioning hadn't worked. So there are areas in Houston with a lot of landscaping and grass growing, trees. That's good. So that means that area was relatively cool. Again, another shot of that electrical supply set into the city there, and see how big that is. Important. This is a view down the street, looking at the trees providing shading to the walkways. So people moving from one space to another has to be in shade. It's almost impossible to walk through a city like this in peak solar times without becoming uncomfortably hot. So the trees are there to give us some shading, and they're relatively small, of course. They need to mature a bit more. I mean, some of the bigger cities, the older cities in the world, like London, have very mature planting down the road. In fact, they start cutting some of them down because they're falling down. But this is something we need to ask for. We as engineers don't provide it, but landscape architects will give us that. And inside Houston was the Toyota Center, which I found to be an interesting place. I didn't go in, but it's some kind of big arena building. I don't know whether they play football or baseball in there or whatever, but it was a big arena, and that was fully air conditioned, although it was enormous. But as I looked at it, I noticed this entrance isn't cool. So you're very hot out here in the street, and you've got to really get inside the building to benefit from the cooling. However, around the building were lots of big grills like this. There's a lot of air being used, and that air was being either pulled into the building or blown out of the building. So this particular one was an air inlet, and you can see it just drags the air in, pulls it down to below to the plant room, and then the air handling plants will cool that air and distribute it around the building itself. And these existed all around the building in whatever way the engineer had set up his air handling plants and systems. But this was interesting. When I looked here, this man has stopped and he stood here for a bit staring at the bushes. And I thought, oh, what's different about this? Well, what is different is that grill you can see at the back there in the wall, just behind the plants, is pushing out cold air. And it's not deliberately cooling this, it's obviously the exhaust air from the building. So buildings like this will have inlets, they will have outlets for exhaust air, The air that goes in will probably be recirculated by 90%. They probably have an air quality monitor on it, so they know what mixing to use. But at the end of the day, some of the air will always be exhausted because we have to replenish the amount of fresh air in a building. When it's fully occupied, by the way, that could be quite significant. It could be working on 50% fresh air. So this cool air that's coming out will spill out of the building here, and it won't rise. It's not hot air, you see, so it won't rise. It will fall, and it will form a pool of cold air on the pavement where this man stood, in fact, and it will spill along sideways. It will obviously mix with other air, and the wind will blow it around, and it will eventually become mixed with the outside air and warmed up, and then it will then drift upward. But for this period of time we're looking at, it sits here as a cold cloud of air on the pavement because it's heavier than the warm air outside. And I thought, this is a great idea. If we deliberately did this in parts of our buildings, we could provide free cooling outside using waste cold air from the building. In order to achieve that, of course, we have to engineer our system so we spill the air out in the right place. But that seems to be a viable solution, particularly when we have big, tall buildings. In terms of the UK, we're looking at getting heating and cooling from our canals. Victoria's built a lot of canals, and many of them have not been used for years, but they're coming back into use, which is good news. People like boating, they like being on the canal, the waterway, but it's also a great source of heating or cooling, or both, in fact, using heat pumps. So it's water to water heat pump, water to air heat pump, if you like, but the water is the source of the heating or cooling. Coming back to the convention centre in Houston, this is the convention centre itself, which ASHRAE had the program in, and you can see there that we were in LEED certified building, which is silver certified, the Green Building Council, enormous space, fully air conditioned, very comfortable. Must have cost a fortune, of course, to cool it. And this is the kind of plant inside that was doing that. But this idea of cooling outside wasn't really embraced anywhere, not deliberately. That instance I showed you was just fortuitous, really, because it had to happen somewhere. I think I could have seen a better place to do it, but they had it under that area. But you can see here in this picture that white duct above coming to the outside wall, and then the air being blasted out there. So it's nowhere near the ground, really. So at that point, it would be heavy and fall, but it would mix through the outside air and dissipate before it had any beneficial effect. So we need to think about how we're going to use cooled air if that's our plan. So I think, in concluding then, that the hot climate design guide is going to deal with hot, dry and hot temperate climates. By hot temperate, I mean the UK. We're getting summertime temperatures of 40, which is very uncomfortable, dangerous even for people. So we need to deal with that. And I think we will look at the arid, the dry component as well, because we haven't got particularly high humidities here, and many people don't either. So the arid section can be quite helpful. It can show us how we can use that dryness to cool the air and run our heat pumps more effectively. So I want to look at passive solar design, pick that up as a topic, as well as our HVAC systems. So we cover both and how they can be integrated. And then through that, we can encourage more hybrid operation. The target for getting this guide published is now 2026. We're hoping to finish it next year in 2025. And then ASHRAE Publications Committee takes it off us, and they will take about 6 months to publish it. So we're authors and they're the publisher, but they won't start publishing until we finish all our writing work. So we have ASHRAE author workshop in progress now. This is the first one we've had for about 3 or 4 years because we stopped during COVID. But thank you very much for allowing this one to start the ball rolling, and I will be organising more of these, and particularly maybe focusing on specific topics. If anyone wants to contribute, just contact me. to help with a chapter or all the chapters, or maybe just review what we're writing, or if you've got a good example to share, please let me know. So that's concluding my workshop today. I wonder if anyone's got any questions or points they want to raise. I'm just listing some things at the back there, and I can give people access to these documents if you wish. Okay, have any more questions and answers?
Thanks, Frank. Thank you very much. I think that summarized it quite well. I'll just give a few minutes for any questions that might pop up in the chat, and I'll read them out.
Okay.
Yeah, just wanted to emphasize, I mean, the whole purpose of having this as, you know, multi-chapter kind of event, and it was good to have it as like a UK Sudan chapter. So I'd like to thank them for also pushing this forward. Is, you know, the contextual element to it, is the multi-contextual element associated with this guide, and how it needs to cover, I guess, all the context, you know, geographical context, cultural and stuff like that. So hopefully that will increase the, you know, the diverse and innovative approaches that are followed in the different regions across the world. So hopefully we'll get more involvement from this aspect. I can see
Yeah, absolutely.
two questions coming up.
Um,
Um,
ah,
the first question was,
Hassan has asked.
yeah,
Sorry, go on, Emma.
yeah, I'll just reading Hassan's question. Yeah, I'll let you read it, Frank.
Hassan's asked, what about extremely hot and humid climates? Well, we already have an ASHRAE hot and humid climate design guide, so I don't want to repeat that, but we will be referring to it and probably identifying specific points in it where they relate to our guide. But if someone's in a very hot and humid region, then the other guide covers that quite well. However, what we don't have in ASHRAE at the moment is a guide for hot and dry or arid climates, um, or people or climates that sway into that. Because you know, if you look at your climate, it could be hot and humid for short periods, then becomes more hot and dry. Depends on weather conditions, that kind of thing. So um, we don't want to repeat the other guide, you see. So that's why we're going to be careful not to overdo that. If you feel the other guide's lacking, by the way, let me know and I'll feed that back. Or if you feel they should be combined, that's another idea. But at the moment, we're not doing that. We're doing a separate guide. Um, I think I'm not sure if Hassan. Are you from Kuwait, Hassan? Ah, Dubai. Yes. Yeah. We would basically direct people to the hot and humid climate guide as it stands at the moment, and we will focus on hot and dry, or hot, you know, towards humid, but not very humid, not extreme. Email ID is at the end of this. I'll come up to the next slide. And the recording is being made, so I think Amma and his colleagues will have that for you. Yeah.
Yeah, so we're
Is
recording the session
interesting.
at the moment, and then it will go up on the ASHRAE UK YouTube channel. So if you just have ASHRAE UK
Oh,
YouTube
okay.
channel, I'll try and put it up by the end of today. So hopefully, in the next few days, you just go ASHRAE UK, you'll find our YouTube channel, and just find the whole recording for this session there, which will include also the names of the guides.
Okay, thank you. That's helpful. Yeah, I think one of the colleagues from Kuwait came to our meeting in June. He was saying that Kuwait had got a hot, which is I put in this presentation, actually got to 54 degrees C, I think, and there's another extreme temperatures. You can't really go outside in those temperatures. You certainly can't do any work outside. It makes life very difficult. So we were talking then about district cooling. So I've been to Kuwait myself, and their drive for a better uh, locations and buildings has introduced air conditioning on a grand scale. Of course, the amount of energy they use has gone up dramatically. So they've finding themselves using a lot of the oil they produce just to drive Kuwait, which is not a great idea, because if you can sell it to the British or someone else, that's a better idea because you make money. So they're looking at district cooling as an option, and a report that they did from Kuwait University showed that if they were to have district cooling across their city, it would reduce the energy use by 50%. So it's a half. So that's brilliant, really. So you're now putting cooling into every building, and this cooling is district cooling and pipe work. By the way, once you've got a pipe system like that, you can use things like night cooling, with efficient chillers much more easily, because you've got your thermal storage in the water. You can have water thermal stores in buildings for resilience. It really opens up things. District cooling is a great way of going, but it does have to be planned in, of course. It removes some of the plant from buildings, but you still need pumping systems and pipe work and controls, of course. But the central cooling plant can be elsewhere. I know Hong Kong is looking at using the sea for that, so that's another idea. Sea cooling. Toronto, for example, uses Lake Ontario, which is renewable energy. It's free cooling because the lake is cold. So that's something we're going to be dealing with in the guide quite deliberately, and we have one of our authors on that is a leading expert in that area, and we're working with TC 6.2 as well, who look after the district cooling. Can the guides be used for India in some cities like Mumbai? Yes, they can. Yeah, I think they'd be okay for those cities. Again, because to some extent, I'm looking at Mahodi tables, which enable us to look at very different climate regions and identify or distill out what are the important issues. Is it about wind movement or shading or insulation, thermal mass, or what? And when we get those things right, we're going down the road towards a much more effective engineering system. I see. Yes, I see, Hassan, what you're going to do. You're going to let me know a little bit more about Dubai, which would be good. And I appreciate your offer to help. So Dubai is in a climate zone 0B, extremely hot and dry. Oh, wow. And therefore, yes. So this is very arid conditions, isn't it? Probably getting on for something like Death Valley in the United States. And would require a lot of thought about how you deal with that. I think we could really produce a material to help there quite effectively. And if you're working in that area, your help would be invaluable, because they'll have solutions they use already. Whether we can help make them more effective, that'd be even better. Okay. Okay, Kim has just written to say that she thinks the district cooling can support a city's energy savings level, and in small clusters as well. You can have small schemes, and then you can link them together and make them bigger schemes. So this is in a way how district heating developed in Scandinavia and other places. They started just in a small area, and then people realized this was a good thing and extended it to other areas. A lot of sharing can take place, which is good as well. We don't want we don't want people to throw away energy when they don't need it, because they could be putting it in somewhere where someone else can be using it, and they can obviously make money for that as well. I think data centers are a classic example of that. How a data center is always cooling itself and tending to throw the energy away. There's been a trend to build them in Scandinavia and Sweden, where they can be in a cold climate and get their cooling for free. But I said to them, well, why don't you put them in a city centre and put the waste heat across into a hospital where they want a lot of heating, a lot of hot water, things like that. So I think that once we begin to understand our engineering systems can help each other, and it's not just a question of helping for the sake of it. It can be financially beneficial as well to sell that waste heat rather than dump it. Then I think we're going down a better road. So it's still early days, but I think the drive for net zero is helping. A lot of people do want to be net zero. It's become, shall I say, fashionable. I think us engineers always felt we could do it if we had the backing and the money. But people are wanting to claim to be net zero. I know Amazon here in the UK have all their deliveries in electric vehicles, and they claim their sheds are net zero by buying energy from a so-called net zero energy company. So they're seeing this as promotional, I guess, in order to do that. So this is all helping us because we can pick up and do our job much more effectively if people are really asking us to give them those solutions, and if they provide us with the right resources to do it. Yes, that's a good point. Surplus energy from a data center, heat which is being dumped, can be put into a heat pump, and it can be used to provide cooling with absorption chillers, for example. You could be doing cooling systems. We've done that at Media City in the UK, or again through the heat pump, providing heating for hot water, hospitals, care centres, and those kind of people. Retail, cooking, restaurants, they want heat. So just because a data center doesn't want heat doesn't mean we should dump it. So I've done a data design for Sweden myself, and all of the heat is thrown away, and the cooling is done by bringing in cold air, which we blend with the waste heat air, push back into the building at the right temperature. But none of the heat is used, which is unfortunate. But in that part of the world, they don't seem to need it. So it's a question here. I was in Mumbai. So I am from Mumbai, but I was in London for 1.5 years for my master's degree. Why do temperature values are misleading? Sometimes even 27 feels like 35 in Mumbai. That's interesting. Yes. Secondly, does this also mean we can use ASHRAE hot and humid guide for London as well? Well, I think there would be periods where you could, certainly. I think with London, there's an added thing called the heat island effect. So you can measure the air temperature, but if you've got buildings around you radiating heat at you as radiated heat, then the combined temperature can feel a bit oppressive. And I think the air quality is poor as well. So when you add all those factors up, it feels oppressively hot. And I guess that's why London at times can feel like you want to get out. I live in the north of England, so I go to London to come back and walk off the train, and it's straight away the air feels much fresher and cooler and a better quality.
I think London as well is because I guess the buildings were built, maybe centuries ago, uh, and then predominantly for a cooling climate. And obviously now we're reaching extreme temperatures, and you're living in a house that is designed to retain heat or suppress heat, then your indoor environment just suddenly becomes very hot because the design was meant to be that. And obviously now with those increased temperature, you just suddenly feel extreme. You feel that heat way more compared to a location which historically has been warm. So maybe that contributes as well.
Well, absolutely right. And people in London find it difficult to sleep now as well, of course, because of that very point, Emma. The buildings were designed for cooler climates, and now they're hotter at night time. The temperatures can be very, very difficult for people, particularly if they're not used to it. So good point, Raj. Thank you for making that. Thank you. Okay, I think that's it's been a great session. I thank everybody for attending, and I think you'll put this online soon for everybody, which I appreciate. And I'll report this back to our committee, our MTG committee, and I'll ask them if we could do some more, maybe in other parts of the world even. But thank you very
Fantastic.
much for this idea. Been very,
Brilliant.
very successful. Thank you very much.
No
Thank you.
worries. Thank you. Thank you for your time, Frank. I think it's been, really good to obviously open this. And also it was good to collaborate with, I want to thank Sudan chapter who came up with the idea of opening up to everyone essentially. And it's good to see, there's points coming from all over the world with specific context. Yeah, so thank you to everyone attending. And hopefully work more with Frank to make those sessions, I guess, more targeted, specific topics, passive house, passive design, active. But yeah, so this is Frank's email. You can see on the screen at the moment. If you want to be involved, if you want to reach out, just email Frank directly, or feel free to email the chapter and we'll be able to steer you to the right direction. So this session is being recorded at the moment. I'm going to close the recording in a bit and then we'll upload it to YouTube, hopefully today. and then you can revisit anything that's been mentioned today from that video recording. It's just the ASHRAE UK chapter. Just type ASHRAE UK and you'll see all the videos that we record. Yeah, thank you very much for attending, and hopefully see you in future webinars hosted by the chapter. Thank you.
Thanks, everybody.